Hi everyone. In this video we're going to be looking at the formal definition of what a limit really is. We'll also practice evaluating some limits, and we'll be looking at the properties of limits. So the first thing I want to draw your attention to right away is the super formal definition here. Good news, we won't work with this really at all in our course, but I'll let you read through it if you want. You'll see there's some pretty fancy Greek letters in there. We've got epsilon, we've got lowercase delta. But basically, let me just translate this for you. It says, as you squeeze the x values down to a certain range, and you can also say, hey, the y values of a function are closing in on something as well. And as we do this for smaller and smaller windows of x, we can say with more and more precision what the y values of a function are approaching. So this whole epsilon, delta stuff, you will probably only see this and have to work with it if you go on to study math and actually pursue a degree in mathematics. I did not get a degree in mathematics. I have a degree in physics, and I never had to work with this. So yeah, that's pretty nice. Basically, again, what it's saying, this is kind of the informal definition here. As the x values of a function approach something, it is possible that the y values are approaching something as well. So as we squeeze down the x values, as I did on the Desmos graph, as we squeeze down these x's, the y value should fall into a very small range. So let's work with that just a little bit. Good news is, on continuous functions, typically the limit of a certain point is usually just the function value itself. So when you're evaluating limit, the first thing I want you to do is to always try substituting in the x value first. Always try substitution first. So let's look at problem A. Problem A says we want to know the limit as x approaches negative 1/2 of 3x squared times 2x minus 1. So limit as x approaches negative 1/2 of, okay, sorry, I have a bad habit. Well, a good bad habit that I picked up as a student of just recopying the problem, even if I'm literally only copying it over 2 inches. Anyway, okay, so let's try substituting in. So 3 times negative 1/2 squared times 2 times negative 1/2 minus 1. So let's see, that'd be 3 times positive 1/4 times 2 and 1/2, we put together make minus 1, minus another 1. Put this all together, how about negative 6/4? Ta-da! This is what our limit actually approaches, because that function is continuous. There'd be no reason for that function to approach anything other than the y value that we can actually get when we plug in the x value. This can change a little bit if there's any sort of discontinuities, maybe holes, maybe vertical asymptotes. And so I do see that this next limit here has a denominator. So who knows? Maybe that'll change something up. Let's go ahead. Let's still try the substitution first. So I am going to go ahead and plug in, oh no, right-click, there we go. I'm going to go ahead and plug in 2 for y there. So 2 squared plus 5 times 2 plus 6 over 2 plus 2, which this is, let's see, as long as we're not dividing by 0, which we're not, this should work out as well. So 2 squared, 4, plus 10 plus 6 over 4. 20 over 4 gives us 5. So we could say the limit as y approaches 2 of the original equation equals 5. Not so bad. There are some special limits that I need you to know. So check this out. I'm going to look at this one here first. The limit as x approaches 0 of sine x over x equals 1. So if we graph this, let's see in my other tab here. Here it is. So the line in red is that function, sine of x over x, and you can see as I take the x value closer and closer to 0, watch those y values. See how they're getting closer and closer to 1? But it can't actually equal 1, right? Or, okay, sorry, my calculator is rounding up to 1 because it only goes 3 decimal places. But if we actually plug in 0 for x, oh, come on, say undefined. There we go. If we actually plug in 0 for x, we're dividing by 0. So how can that produce something that's 1? Well, here's the thing. The function's value is actually undefined at that place. But the y values are approaching 1 from either side. So that's why we say the limit evaluates to 1. If you are happy to wait about 9 or 10 months, we'll eventually have a way of proving that this limit actually is 1 algebraically. So this is one I need you to know. This next one I also need you to have memorized. This one's a little more fun here. Notice x is also approaching 0 again. This time we have a ratio of sine functions, sine of ax over sine bx, and I also have that one pulled up here for us to look at. So I'm going to turn off this one. Turn this one on, please. Thank you. Okay, so let's see. Let me zoom out, zoom in a little bit here. And you can see, so look on the left. See, I've got these sliders so I can, oh no, it kept moving. Sorry, guys. As I play around with the slider, I'm just changing the a and the b value in the function. So if I make them the same, that'd be sine of 3x over sine of 3x. Well, of course, that's going to be the same thing everywhere. But, you know, if I increase this, maybe decrease this one, this would be sine of 4x over sine of 2x. And check this out. As x approaches 0, there go our y values, closer and closer to 2. If we actually get there, it's going to say undefined. Same thing on the other side, closer and closer to 2. 4 divided by 2 gives you 2. If we make it something weird, maybe sine of 4x divided by sine of 3x, you can see getting closer and closer to 4/3. It'd be like 1.333, which we're real close, undefined. Bam. Weird, huh? So that's another special one I need for you to memorize. Up next, limits have a whole lot of properties. So basically, if you know a limit of a function, you can compare it to other limits. You can add them, you can multiply them, et cetera, et cetera. So I'll just run through all the limits real quick. All of these properties are based on both limits existing. So notice we have the limit as x approaches c of f of x goes to some number L, and then the limit of a different function as x goes to the same value. Notice in both of these I said x goes to c equals m. So if we're combining, so like look at the first one here, it's the sum rule, f of x plus g of x. This rule only works because both of them approach the same x value c. If you're combining the two limits in the sum, you can just add their original answers together. So limits can be added. And if they can be added, well, subtraction is just the opposite of addition, so they can also be subtracted. The product rule says if you have one function times another, the limit of the first function, well, I just kind of screwed that up. I'm sorry. If you have two functions multiplied and you know the limit of each of them individually, you can just multiply those two limits to get the limit of the product of those two functions. So limits can also be multiplied. This rule we use a lot. The constant multiple rule, it says if you have just a number, whether it's 5 or 17 or pi, times a function and it's inside the limit, you can actually take it, you can pull it out front. Whether it's k times limit of f of x, okay, we should probably write our x approaches c here, or its limit as x approaches c of k times f of x, makes no difference. The last one is the quotient rule. Just like how you can multiply limits together, you can also divide them. There is a little footnote here. The limit of the denominator, so the limit of g of x, can't be 0. So otherwise you end up dividing by 0, and we're going to have to look at some other trick to evaluate that limit. So let's practice a little bit with those properties. I've got some sample problems on the next page for you. Assume that the limit as x approaches b of f is 11, and assume that the limit as x approaches b of g is -3. And then we've got 3 problems that we're going to try and do first. Okay, so problem A has us evaluating the limit of g cubed of x. But wait a minute, we didn't have any exponent limit rules, did we? Well, sort of, not really. Isn't this really the same thing as saying g of x times g of x times g of x, which we did have a multiplication rule, so we can actually go ahead and do this. So it's really going to be the same thing as limit as x approaches b of g of x times, I think you get where I'm going with this, limit as x approaches b of g of x times, one more for good measure, or because it's what the problem says, which is going to be -3 times -3 times -3 gives us -27. Problem B has x approaching g and f of x times g of x. We did have a multiplication rule, so we can say that this limit is the same thing as limit as x approaches, x approaches b of f of x times the limit as x approaches b of g of x, which would be 11 times -3, gives you -33. For part C, we're going to have to worry about a few things. First, we're going to have to split the limit up along the addition. So it'd be limit as x approaches b of f of x plus, now I'm also going to use the constant multiple rule on this 4. Let's say that's actually 4 times the limit as x approaches b of g of x. So this would be, let's see, the f1 is 11 plus 4 times -3. Should be 11 minus 12 gives you -1. Okay, so what do we do if we just plug in the thing like we said earlier and it doesn't work? One of the most common results that we're going to get is 0 divided by 0. And no, it's not 1, and it's not necessarily undefined. Okay, I mean, really, 0 divided by 0 is undefined. But when we're hitting it with the limit operation, remember what we are worried about, what's happening as it gets close to 0 divided by 0. So when you're evaluating a limit, 0 divided by 0 is technically an indeterminate form, which means you can probably do something else to try and evaluate the limit. If you get a number divided by 0, so see how I said a divided by 0 where a isn't 0 itself, that usually means you've probably got some kind of vertical asymptote, and you should just look at a graph or sketch a graph if you can. Let's look at the first one here. So if we just try and substitute right away, we'd get 0 squared minus 3 times 0 over 0 squared minus 4 times 0. Whoa, that was weird. I did not mean to do that, and I don't know why my computer's doing that. Okay, 4 times 0. Well, surprise, surprise. He mentioned it up here. Hey, we had an example about it. 0 divided by 0. We can probably do something else here. How about, let's try a little algebra on it. I see a greatest common factor in both sides of the fraction. So why don't we factor out a t? Now we can reduce just a little bit these t's. No, why are you doing this? We had it so good. It was going so well. There we go. Okay. Train of thought. Here we go. Limit t approaches 0 of my reduced form. Now let's try substituting again. So 0 minus 3 over 0 minus 4 gives you -3 over -4, so positive 3/4. Hey, that is the y value that this function is approaching. In fact, there would be a removable discontinuity at that point. Let's try again with the last one. Okay, it's getting real frustrating how you keep scrolling up, computer. I'll have to figure that out by the next video. Okay, so again, try and plug in 3. I think you're going to wind up with 0 over 0 again. So let's try something else. Limit as x approaches 3. Okay, this time we have a pair of quadratics. So let's try factoring. Let's see, we got the 2x squared. How about minus 3 minus 1? I think that'll work. Yeah, it works. And then let's see, plus 3x minus 18, x minus 3. What? X minus 3, and then x plus 6. Okay, how did that help? Oh, there we go. I see this thing we can divide out. Bam! Divide it out. Equals limit x approaches 3 2x minus 1 over x plus 6. Now let's try substituting again. So we put in 3 up top. We've got 6 minus 1, so 5 over 3 plus 6 is 9. Looks like our y values of the original function are approaching 5/9 as x gets closer and closer to positive 3. In general, again, if you have 0 over 0, you should be able to do something algebraically, some kind of simplification to get to the point where you actually can substitute the number in. If that doesn't work, well, it should. Basically, the only time that doesn't work is if I give you a problem that we can't solve yet, and we will have other methods of dealing with 0 divided by 0 in the future. Happy face. That's it for this time. Have a good one.